So hello guys, welcome to the workshop Code to Chip. So what exactly we'll be doing today is writing some basic code in HLS, which is basically using a C and C++, and we'll be generating a .v file, and then Suhas will show you guys how exactly we can use this .v file and convert it into a layout using your OpenLane, right? So let's get started. So we'll go through a quick 10 minutes of an overview session where we'll understand basic theories that will just give us a very good brief idea of what HLS is and give us a motivation of why we need a HLS. And then we'll go ahead with the lab, and then Suhas will be showing you guys the how to use OpenLane. Right. So we have a traditional embedded system devices where we have computers, and these devices are used with softwares which are supposed to be maintained. And then what we thought was, I really don't want to maintain the software. I would really love to use someone else's computer, which is way far powerful than mine, right? So that's where the whole concept of cloud came in. So these are run by organization who actually give you these services, and you're gonna get paid for it, right? I mean, you're gonna pay for the services, and in return, there you can use their computation resources. Your Google Colab is a cloud server, right? We can run codes and stuff. So that's then when this whole notion kicks in, we realize, right? Now we wanna run something on another computer. What exactly is going to happen is you need more bandwidth right now. You need to send more data. I mean, we have seen this in case of Google Stadia as well. That was a whole reason why it failed, right? Because we didn't have enough bandwidth to send all the data from your computer to the Google server that we can run game. And but there are cons of cloud computing like data privacy, security, larger bandwidth requirement. So this is where your whole concept of edge computing comes in. So your edge devices, I mean your end devices are basically like, they are connected with sensors and actuators. So your actuators are going to help you take some action against the environment, whereas your sensor senses something against the environment. We are not going to go much into this, but what we are most interested in is this connection out here, end device and your edge. So what your edge device basically does is it's responsible for involving in very small decision making. So it is a light intelligent model to take some model to basically control your IoT. So I guess we can understand with an example. So let's say I'm gonna ask you to train a machine learning model. So now you can't do that really in a very small Intel Pentium chip, right? So, but if I give you a whole server, you can do it, correct? So now what you can do is you can train your whole model in your cloud and basically try coding that in HLS, convert it into a hardware, and you can make that as an ASIC or an FPGA and connect it with your end device. So I hope you guys are getting a whole idea of where I'm going with this, right? So edge computing actually introduces security, low response time, and data privacy to the cloud-based application. So these are going to act as an intermediary between these, and you can even take an example of your automated car as well. So let's say radar and point cloud data are hard to be processed in your processor. So you can use an edge computing device that can help you do this task. So when I meant edge computing device, it's just gonna be your ASIC or your FPGA there. So just to give an overview of what your FPGA can do in this 3-layer, I have included this slide in this small lecture. So your end device can be in your end device FPGAs can be used to directly interface with sensor and give signals to your actuators in a hardware level. And when you go to edge, a hardware that can basically perform some task that the processor is really slow with. And then we come to cloud device where FPGA find most of their applications in even today. We can use them to accelerate database oriented management or yeah, sure, whatnot, right? So now we come to the main topic of our discussion. What exactly is HLS? So HLS can be used to describe design algorithm and logic circuits on end device, edge platforms and cloud servers. Just a very basic example out here. So you have your C or C++ files, which is going to be given to your HLS tool, and it's going to generate a .v file. And now, when I mean C and C++, there can be other languages as well. Like there is this new HLS language called XLS that's coming up, and that is going to be using your Rust. This .v file can now be used with your Vivado or whatever EDA tool you're comfortable with to visualize the RTL and time flow. So we'll be using Vitis out here because Vitis is a good platform to get started with for beginners. We'll see it in quite a bit, and we have already introduced the notion of FPGAs, and we know what exactly .v files are. Right? These are Verilog files that can be dumped into these, and we can even convert them into a layout. So your Vitis unified software platform gives you this option to basically design, develop, and debug and synthesize in C++ or C. You can even visualize your it can give you like your whole report as well, where you can see how many LUTs are being used, what's the temperature, and so on. So your C++, HDL and OpenCL. So when I say OpenCL out here, actually your FPGAs can have a processing unit and LUTs in the side. So your OpenCL can be used to interface kernel. We have actually discussed about these concepts in our CUDA sessions as well. But anyway, so you can not to deviate much. Today we'll be designing a very simple ALU anyways. So yeah, so Xilinx provides us a whole stack of edge AI and other libraries like DSP, cryptography to help us out with this process. And in the end, whatever .v file got generated, we can use a FPGA module to basically deploy the circuit that was synthesized. So I won't be explaining these in much as we have a very short period of time today. We'll be looking into this soon in the later sessions as well when we are discussing about pragmas. Your design principle where your producer consumer paradigm comes in. So I'll just give an overview of producer consumer paradigm and pipelining because these are stuff that we'll be using a lot. So basically, let's say you're a student and I ask you to go and collect information of all other students and their marks. So, and then you need to add all their marks and you need to export the data and give it to me. So that's what it's given out here: import data, process data, write output and export output. So what you're going to do is you're going to import the data. You're going to go student to student and ask. So I don't see really where we can parallelize this. So we're going to skip this over. Process data, where you're going to take this data and add it. It's going to take some time, right? And then writing is also going to take some time. Let's say you want to format all these into, let's say, bold, italics, whatnot in your Excel sheet. And it's going to take some time there too. But now what I'm going to say is that instead of doing all this step by step, you can parallelize this. Like basically when you're collecting this your student 2's details, you can process the student 1's details. Like you can write the outputs of the student 1's details. And then in the end, you can export the data. That's what the overlap means. And we all know what pipelining does and how it improves the throughput of our whole system. Not going much into detail, just giving an overview. The diagram is self-explanatory. We see that how the sequential latency is going to come down significantly out here while increasing the throughput. Like basically in the third clock cycle out here, we can see only one instruction is being run. But when pipelining is done, there are 3 instructions that's been run out here. Right, so we'll be looking into all these later, basically when we are discussing about pragmas and stuff for loops and so on. So now we'll be going into the demo session where we'll be making our ALU. So today it will be exporting the tool and making an ALU, and soon we will make a conduct a workshop on using math functions and other oriented stuff, like basically doing stuff like let's say optimizing using function inlining and root control, right? So over to the demo session. So hello guys. So now we are done with slides and we know what HLS is. So we'll be going to do some basic programs, and we'll be synthesizing an ALU circuit as a part of the lab component today. And I'll be showing few other codes as well, but we won't be doing them in detail. So let's get started. So I'm gonna go ahead and create a project called, okay, ALU is our project, and let me go to the, so right now what we have out here is basically an option for us to add or remove a previously made design file. So if you have already made a previous design file, you can import it into the IDE using this option out here, add file and new file. However, even if you go ahead from this, you can add it at any point, right? So I'm gonna go to the next one, and then again, similar to your design file, you can also add your test benches that you have made in C or C++ into this. So a small description about test benches is that you might be familiar with these from your previous HDL classes. However, your test benches are nothing but a separate program that are used to force inputs into your circuit, and you're gonna simulate it and you're gonna get some output, and we can verify the functionality of your circuit, right? So we're gonna go to the next one out here. I guess gonna go with this itself. I'm gonna choose a RTX 7 board. Okay, so it's gonna set up a project for us. Okay, so the project is created. Now I'm gonna give an overview of what our IDE is. So for version control, we have your Git repositories out here, so you can even import your repos and stuff. So you're gonna see all your modules and loops out here. You can do code simulations. And then you have your warnings and errors. So generally, if you use a normal GCC compiler, it's gonna get printed in your terminal, but your IDE gives that option out here. Again, flow navigation is given out here. We won't be looking into that, giving much of importance. So let's see what are the files that actually got generated for us, because these are the stuff that we are going to be using, right? So we see that there are a lot of files, .h files that we have out here. So these are C++ headers that we are going to be using. We'll be using a couple of them today as a part of our mini project. So anyways, so we see that there is something called a source and test bench. So under source, I'm going to go ahead and create a new source file since we haven't added any. So we see a save as dialog box up here. So I'm gonna name it alu.cpp, and let's save it. And okay, let's go into our test bench and create a new test bench as well, alu underscore test.cpp. Okay, amazing. So we see that each of them have their respective files. So let's go into our main file now. Alright, so what exactly we'll be doing now is to create something what we would call as top module in our Verilog or system Verilog. So these are going to tell us what inputs and outputs we are going to have, right? So if you are familiar with that, you should be knowing the term called as top module, right? So in similar to that in HLS, we call it as top function. Okay, anyways, we can go ahead. First is we give the return type. So R is going to be return. Okay, let's create a very simple adder to get started with. So int, and it's going to be ALU, no, we are creating an adder, so let's name it adder. In A is going to be our input, in B is going to be our another input. You can store the value in C and in another variable called C and do it. However, since it's just two variables, you can just directly return it. Return A plus B and a semicolon out there. Right, so this is a synthesizable circuit. So now what we have to do is we have to go and actually add this top function into our project settings out here. So I'm going to go into synthesis. I'm going to browse. So we see that under our file alu.cpp we have something called as adder, right? Okay, I'm going to add it. So if I actually create something called int sub int a comma int b return a minus b, we can go into the same project settings and see that browse, we see that a sub has also occurred, right? So however we'll be using only the add, so I'll be removing this, and we have already added the top module. So I'm gonna go here and I'm gonna run synthesis. So which means it's gonna generate a Verilog file out of the C code that we have written. In case of your simulation, we'll be using a test bench, which we'll see in a bit. So yeah. Alright, I have to save this since I modified it. So just give it some time. Okay, so our synthesis is over and we have our synthesis report out here. So we have some timing estimates out here, and we see that we haven't used any pipeline. Well, yes, we haven't gone with a loop as well, and we'll be utilizing 39 LUTs for that operation. And we see that we have some ports, hardware ports out here, A and B. Well, you can go on and read all these. These are going to give more and more information on the synthesized circuit. But what we are more and more interested in is the synthesis file out here, folder out here, my bad. So under report, these are the reports that's going to get stored there. But under Verilog, we see that there's a Verilog file and we have a VHD file for VHDL. So let's just open the Verilog file because it's going to be easier for us to read, right? So we see there are some additional signals that are actually created for us, and you can actually import this into Vivado, and you can visualize this in the form of RTL, the .v file. Suhas will be showing you guys how to convert this into a layout. Okay, but what do these signals mean in terms of our Vitis HLS, right? So basically your AP start means it has begun compute, so it signals a high when it begins the computation, and when it finishes the computation AP done signals high, and when it's not started your AP idle is high. Actually, there is supposed to be an AP clock as well out here, but since we don't have any synchronous logic in this, that signal has been not generated. So for ready for the next input, we have our AP ready signal. So since now that we have done analyzing a very basic HLS file, we'll go ahead and do our mini project where we will be generating our 3-bit adder, right? So I mean 3-bit ALU, my bad. So we'll be just implementing a plus and a minus because it's implied that you can use star for multiplication, percentage for your modulo, slash for your division, and you can use the same bitwise operator that you would use in your C as well, right? However, I forgot to mention a point, right? So out here we see that we have directly mentioned int, and that is why we see a 32-bit signal has been produced for your A. So which means you'll be having 32-bit input, 32-bit input again, and then you'll be returning a 31-bit output. So you can actually store this in C variable and see its optimization. It's not the most readable Verilog code, but we shouldn't be forgetting that this is a generated RTL for us, right? Okay, so anyways, let's get started by for making our ALU. So I'm gonna include something called as ap underscore in.h. So this is a header file that is going to allow us create a custom size variable, and we all know how important it is to have custom size bit. So we'll be returning unsigned integer of maximum size of 3 bits, right? So ap underscore un3 does the job for us. Simple. No. Okay, we'll name it ALU itself. And now I'm just gonna copy this. Right, I'm gonna copy it 3 times because we'll be needing 3 signals, right, for our ALU, because we'll need one to control if you wanna add or if you wanna subtract. So in A, in B, and we don't need 3 bits for that. We would be needing just a single bit. So this one would be our C, representing control. Okay, I think our function definition is perfect, so we can go ahead. So I want to go and create a condition. So if C is equal to 0, we want to add, right? And we return in A plus in B. Else we want to return in A minus in B. Okay, cool. So right, we have created our normal file, so let's just synthesize it and check if it's working fine, if it's a synthesizable code. And then we'll go ahead and create a test bench. Okay, there are a couple of errors. We gotta see what they are. Oh yeah, so we forgot to change our top module name, so I'm gonna go here and browse again. Right, so we see that there is no more add out here because we have removed that function, and since ALU is the top function we need, we're gonna include that. And I'm gonna run the synthesis again. Alright, so we see that the synthesis is done. You can get all your reports out here. So we see that LUTs that we have been using is 25. So this time our code got optimized way better than the last time. So now let's go ahead and create a test bench for our ALU. So I'm gonna include ap underscore in dot h. Hashtag include stdio.h because we'll be printing it as well. Okay, just give me a second. Let me pull in the program since we're taking too much time. Okay, so let me quickly explain what exactly is happening here. So this it's not simple ALU. In our case, it's just ALU. So we see that from this unit out here, we have just basically copied the function definition and reinstantiated it out here. And we haven't used an op signal, we have used a C signal. So now we have just declared all these as AP underscore event. So these all are going to get converted into 3 bits. And then right out here, we have just used a normal C programming, which is going to be done by a GCC compiler itself and in A and B, and it's just going to get added. This is going to get subtracted and going to show us the result. And then we have just created a temporary variable called result add and result sub, which is going to have the outputs given by our ALU out here. So it's going to throw error if I don't remove this simple. Yeah, so now it's actually going to take input whatever output this ALU is going to give and store it in as variable, and we are going to print it. It's very similar to what a C programming does, and that's why it helps us create a very complex RTL very quickly, right? So if I go and if I do a C simulation, shouldn't be having any errors. Gonna save us some little bit of debug time. Okay, well, so if I just pull this console over, we see out here, right? So we can say that we have done a very good job out here. Okay, there's a very small mistake that we have done. Okay, yeah, so basically this is supposed to be 0, this is supposed to be 1, and now it should be working just fine. Let me just quickly simulate this again. So we see out here the inputs are the outputs are matching, so which means that our circuit works just fine, right? So this brings us to the end of our session today. In the next session, what we'll be doing is we'll be looking into something that is called as pragmas. However, I don't want to leave the introduction to the next session. So let me just show you guys the documentation out here. So so you can see out here that we have few set of pragmas. So what are pragmas? Like these basically tell the HLS compiler that you have to perform some changes to the program's regular flow. So it actually makes Vivado HLS act differently. Whenever we create a vector on top, we can actually say that pragma HLS interface AP memory, and it's gonna create a RAM out of it. Or if you're gonna say AP underscore FIFO, it's gonna create a FIFO out there. Right, so there are a lot of HLS. We'll be using few of them for optimization as well. So pragma HLS inline is gonna do function inlining, and you have unroll which is gonna do loop unrolling. So these are optimization techniques, and by default you can include pipeline and specify the pipeline in the config file. So by default for every 64 loops, I guess it pipelines. You guys can refer to this documentation as well. We'll be doing this in the next session, where we will be using a loop to do a vector adder, and we'll be pipelining it. And along with that, we will also look into a small math.h module, which comes along with the HLS to do some certain math functions. And as a part of the final project, we can create a small image processing module. We can calculate we can basically create an image filter which is highly parallelized, right? So with whatever you guys have learned, you guys can go and experiment with the tools today, and we'll be looking into more in the coming up sessions. All right, I'll pass over the video to Suhas, and he'll be explaining the open lane flow. All right. Thank you.
Hey folks, my name is Suhas, and this is the second part of this workshop, Code to Chip. In the first part, Joyen introduced you to Vitis HLS and a few essential um, basic information about FPGAs, high-level synthesis, and why high-level synthesis is essential um, in the current trends. Right? Um, to put it simply, OpenLane is a big compiler, right? So what we do with Vitis is write high-level code like C, C++. Some HLS even support other languages like Python, Scala, and so on. There are a few exotic HLS languages like Pipeline C and a few others that are worthy of exploring. But yeah, the whole significance of writing software to define hardware is for the ease, and also there's been a bit of a paradigm shift lately in the design philosophy when it comes to chips, which I will be talking about through OpenLane. So before that, like I mentioned, OpenLane is considered a big compiler in that sense because compiler basically boils down your code to put into binary, to put it very simply. OpenLane does the same, but in terms of hardware descriptive languages. So you write Verilog, system Verilog to describe hardware or hardware logic, like AND gates, or gates, not gates. Again, simplifying it extremely for the ease of explanation here. But uh, pretty much, OpenLane is a big compiler to give out the final physical design layout, which is fully automated. But you still get the sense of control by OpenLane. So let's take a look. Okay, about the paradigm shift in the chip design philosophy. Um, so as of late, there have been engineers who think software and hardware shouldn't be, you know, two different things where two different set of people are working on something. This is where people believe that to write for your hardware to run certain software better, you either start with the software or you start with the hardware and you develop the other one around it, right? So let's say if that we have a problem in mind, let's say we want to run a certain algorithm pretty fast. We work on what that algorithm requires, right? There might be a certain few things that it might require in terms of hardware to run it fast. So you might have heard that machine learning languages are run faster on a certain set of hardware, right? Like tensor cores or any other specialized hardware, or simply put, ASICs, application specific ICs, integrated circuits. So that the whole thing about developing software hardware is what we want to showcase with HLS and OpenLink. So through HLS, you write code, you get an RTL out of it, register transfer level, or the HDL, the Verilog file, which you can place in the OpenLane and get the full design, right? So that's the whole paradigm shift in terms of the design philosophy. Moving on. So what is the whole point about having open source EDA tools? Right? Um, so there have been changes with the industry having lot more open source development tools, as well as a few popular open source and open architectures when you want to build a process. One of them is RISC-V, right? Um, Having an open source EDA tool and the whole environment of open source EDA enables people like us students as well as developers, small budding startups to not invest a lot of money into EDA because, as you might know, these tools are pretty expensive to license. And having something like a free and open source EDA tool is quite the boon to learn and to develop on your own. It makes designing an IC or a chip way more feasible for students like us. So that's the whole point of it. And OpenLane is one such EDA tool that I believe is one of the best. Okay, this is a small excerpt from a meeting that I attended. This was a session from Triple IT Bangalore. They had a session where they brought in a few people from the industry, and they explained how they used OpenLane and other EDA tools, open source EDA tools, to develop their own, you know, processors or hardware in their respective industries. We saw a few folks from Google, a few folks from this company called Chip Alliance, telling how having open source EDA is quite beneficial for them. In this case, they have configured or tuned an RISC-V SoC, system on chip. Uh, Shout out to my own workshop tomorrow, which is again on system on chip with RISC-V. But here you can see the design and all the tuning, even the fine tuning is being done using open source EDA tools like OpenLane, which is quite interesting. Going on. So this is more of a technical answer to what OpenLane is. OpenLane is a tape out hardware flow, hardened flow that addresses two main use cases. Sorry, hardening a macro and integrating a SoC, right? So again, hardening a macro is basically you defining the hardware to be generated in a certain way. So let's say you want to use a few library cells that you have defined, like the AND gate, OR gate, NOT gate, whatever gates that you have defined, the standard cells. You're telling OpenLane to generate your layout in a certain way. Again, the documentation to OpenLane is a beautiful thing. I would suggest if you are interested in using OpenLane for the hackathon or just in general want to use it, learn more about it, it's a beautiful tool. It's pretty easy and straightforward to use. Okay, yeah, like I said, simply put, it's an all-in-one solution where you give RTL and you get the GDS2 file, which is a layout. Okay, as you can see here, this is a layout of an open RISC processor. So as you can see, there are different elements to it. So it's like a proper chip design being done. And fun fact, you have to just give the Verilog file and this generates the entire thing, right? You can fine tune it. You want a size to be smaller, you can. You want it to perform at a higher frequency, you can. Power estimation, static timing analysis, all of it bundled into one amazing thing called OpenLane. So like I mentioned, GDS2 is just the layout file. So that is the whole format of the layout file. So like I said, OpenLane does everything from logic synthesis, placement and routing, which is placing your logic cells onto the chip, and post-placement optimizations. Let's say you want power optimizations and other evaluations such as static timing analysis. It does it. It automates the entire process. So here on the left-hand side, you can see a small, very simplified flowchart of how it does it. You give the hard macros, you give the user design, which is the .b file you get from the HLS after you generate HLS to HDL, and other files that you can define, such as spice and left, any other Liberty library files you can include in this. And it keeps going on to doing other essential things before you get the GDS. So, moving on. So what is OpenLane? Continuing from what I spoke about from the previous slide. It also uses other open source tools like OpenWord. OpenWord is pretty much OpenLane, but a GUI version. And yeah, it's part of the same thing. And Yosis, ABC, these two are used in conjunction. Yosis is a tool used to synthesize HDL. So let's say you have Verilog system Verilog files, you can use Yosis to synthesize. You do not need any proprietary tools to synthesize this HDL. You can use Yosis. And ABC, which I've not mentioned here, goes with conjunction with Yosis, is a logic optimizer. It is from UC Berkeley and it's open source again, which optimizes the logic. Let's say you have defined a few wires that is not really required in the code, it will take care of it. And a few other things like OCD, OpenOCD, and other stuff that is all packed into OpenLane. So this is pretty much the full stack development when it comes to hardware, right? Just like how you have on software where you have backend, front end, all in the same thing. This is pretty much the entire thing. Fun fact: we do define certain things as front end and back end and hardware too, and this is the full stack that does everything. So in this case, we consider front end to be the HDL part and the back end to be the physical part where we do the placement, the power analysis, and all the nitty gritty stuff when it comes to physical transistor design, right? Okay. So there has been a few successful tape outs of a few RISC-V SoCs called Strive. Um, Strive is again, I believe, is an open source RISC-V core. They have taped it out, which means that they have it on silicon. So they generated a silicon chip out of the GDS2 they got from OpenLane. Yeah, so this is a bigger, a more verbose diagram of how the whole macro hardening happens. So as you can see here, this is the design that you provide. I think the image might be a little blurry, but yeah, let's work with it. So the PDK is what provides the library or the standard cells. Right? So let's say you want to use the final GDS2 to have certain nanometer transistor sizing. So you can have open source PDKs for that. So in the demonstration that will be shown later, I believe I've used the Skywater 130 nanometer technology. That is the PDK I've used. So let's say you want to like that is going to silicon, it will be done in the 130 nanometer process. So yeah, going on, you see there's a step by step of each of them. So the whole magic of OpenLane is that all these individual things that you see in between are all different open source tools. Like I mentioned, Yosis, ABC, used for logic synthesis. All again, they're all just an interconnect of multiple tools, open source tools to get this running. Right? You can see Yosis, ABC, OpenHDF for static timing analysis. So you want to check if you're having any timing issues with your logic. You need so people who do not know, your let's say you design a circuit, it has to perform within the clock constraints that you give. If it does not, it will cause issues in terms of the data not being available at the right time. Since we don't live in an ideal world, we do have a lot of delays, and OpenSTA will take care of those violations and let you know. Design for testability, there is an open source tool called Fault, which will modify the netlist in case of any faults that it can collapse. And yeah, it will basically simplify the circuit to reduce any faults that can be shown post silicon or post fabrication. So OpenRoad is again just part of OpenLane where you can use it for it's used for flow plan placement and routing algorithms. So you in an IC there might be a lot of wires, and routing them is the biggest problem since it takes up the most amount of space. So routing the best way possible in a given area is really essential, and OpenRoad does that for you. USS does an LEC, which is logic equivalence check. So it checks the logic even after placement. It should have the same logic. It shouldn't change the logic that you have defined. So it's more of a formal check that you do through LEC. Triton root again more of a detailed routing. Magic and NetGen are two amazing tools which give you the entire physical verification in terms of doing design rule checking as well as LVS. And GDS2 is streamed out by Magic. So all this amazing things that you heard about OpenLane, and let's say you want to use it, we have a few prerequisites for you to follow. So I would prefer people to use Linux or Mac OS because it's much easier on this. But let's say you are a Windows user and you want to use this, you can use something called Windows Subsystem for Linux to make the installation easy. You can use you need Docker, so you need to install Docker, and you need Git, Python 3.6 plus, preferably 3.8 or 3.9, and make. You need the make to because there are a lot of make files in within OpenLane. Okay, so these again a few other simple installation guides. This will be shared in the description, and a few references that I thought would be useful for people. So yeah, that's about it. I will be linking an old demo of mine for OpenLane. where I've shown how you can add your custom design to OpenLane and a custom config of your own to get run the code, to run the Verilog code and get the GDS too, pretty much. So that's about it.
Okay, this video is to show how to use OpenLane and how to add your own design to OpenLane. So let's take a look. So let's go to OpenLane, and if you have installed OpenLane fine, Docker fine, you should know how to run the first basic test, right? So I think we run SPM for the first time when you install OpenLane properly. So as you've seen before, flow article is the main script that runs OpenLane and runs everything, be it synthesis till the end layout to get the GDS file, right? So instantiating a new design is a bit different from running the basic designs, right? You can't just add your files to the design folder, and it's not like that. So there's a certain way. So let's take a look at that. So before we go for that, we have to make mount, right? So once we make mount, we can go for flow article design. Let's do a simple mux, right? 221 mux, and you have to give this flag called init design config. So this will generate the config file and create a new directory for your design, right? So once you see this verbose statement saying successful and the config file has been created, we can go to that, right? So this directory is not found in the designs directory at all. It will be in another directory called OpenLane and mux21, right? So here's the config. So let's take a look at the config. Let's switch to another one for this. Just a minute. Documents, OpenLane, yeah, mux. So config JSON. Yeah, so this is a very basic JSON file. These flags might not be enough to run to OpenLane properly, so let's make some changes later on. So now we can make some changes. So let's add dir src and mux21.v. okay, why v? We stick to Verilog because Yoast does not support all the constructs available in system Verilog. So just for the ease of it, let's stick to Verilog. If you really want to run or write system Verilog code, I suggest you convert the system Verilog code to Verilog using sv2v, or just write Verilog, plain Verilog, just to avoid the hassle. So yes, so let's save this for now. Let's come back to this later. So we have seen the file now. Oh yeah, now let's create an src file, right? src directory rather. So within the src directory, let's create the mux21 via Verilog file. Okay, let's write the mux21. So input a, b, and s, right? And output y. Yeah, it's all one bit. Let's just assume with that and go ahead. So assign, let's use a conditional operator. So y equal to s will be b or a. So n module. So yeah, now that we have created this file, it should reflect here in the Docker image as well. So yeah, we see it there. So to go ahead with this, we can run flow article design, give absolute addressing, right? You give OpenLane mux21, it should read it from here. So let's give it a run. It shouldn't run. There might be a few issues that you might come across, so let's try fixing that. So as you can see, we already come across a warning saying the core area is too small and the power grids will be scaled down. Okay, this is just a warning, but here we encounter an error. Okay, so this error is from the PDN step, saying the pitch is too small. So here it's taking default pitch. So let's give it a pitch value in the config. So as a boilerplate config, we can take a look at a different design, right? So let's go to inverters, and in this JSON file we see the die area, we see the V pitch and H pitch values, right? So let's take this, right? Let's just copy this. OpenLane, Nox21, and JSON file. Okay, so let's insert that. Yeah, so yes, yeah, and let's insert the die area one as well, right? Okay, that's weird. Okay, that works. Okay, let's save this and quit, right? So cd OpenLane back to that, and let's check the config again. So this is the config, right? So let's give this a try now. So with this, the changes that we have made, we have given a pitch value that it can take. So let's see if the pitch changes in the PDN stage. So let's take a look. Okay, so the pitch doesn't seem to be changing. So okay, let's start meddling with the values, right? Okay, so let's change diarrhea to 35 and see if that makes a difference. Let's see if the pitch changes at all. Okay, doesn't seem to have changed. Okay, I think we're missing one of the flags, but okay, let's open OpenLane, designs, inverter, and config.json. So I think we are missing, yeah, FP sizing. So let's pick that up and go to, yeah, right. Okay, yeah, so let's see if this makes a difference. Okay, so now we see that the pitch value is taken to be absolute, and it's being picked up from the config file that we have given. So previously we saw a value of 1.2650, right? So here we see it's 5.98, so there's an increase, and it should be at least 6.6. So let's nudge the value up to be that, right? So let's change this to 36 and see if that makes enough of a difference for us. Okay, definitely we are much closer. Okay, so one other tip is that as you can see, this is the runs directory, right? You get a lot of runs, and while you're testing it out, you seem to rack up a lot of these, and one way to clear these out is to run this, and it should theoretically clear out everything. So wait, let me just check. Okay, it doesn't seem to be clearing out here, but yeah, I suggest you delete these, so it'll be easier for you. So let's just delete this runs folder itself, just for simplicity's sakes. Yeah, so So let's change the config again. Let's make it to 37 and see if that makes a change. Yeah, so let's run it again with the new values. We're still getting the warning, and pitch is very close to being the minimum of 6.6. So let's keep changing. Let's keep nudging it up. So let's try 38. 38 should be sufficient, but let's give it a try. So we have cleared the PDN stage, and this run should get all the steps covered. So yes, so if you ever come across an issue with the config, I suggest you take a look at the existing config files from the other designs and try to implement the same within. So it usually works out well. It might not be the best optimization, but you can use this as a boilerplate for your config, and work yourself up, make it much better, right? Improve it as you go. So as you can see, all the steps are running, and we should have the GDS file in a couple of seconds here. So yeah, there you go, we have GDS, and yeah, DRC and LVS, and the flow is complete. Okay, so we still have a warning saying the core area is too small for power grid settings to be chosen. Power grid will be scaled down. Okay, so this is there's certain things that it can't do since the core area is too small. So we can mess with that a little later. So to see the reports, let's head over here and go to runs, right? Yeah, so we have two of them, much better than before, but still let's open the latest one, which is 59. Okay, so let's head over to results, final, and before that we can take a look at some reports, right? So we have the metrics.csv, and yeah, I don't have the thing to run it, but anyway, I'll just show you the GDS file. So to run the GDS file, let's just go to OpenLane mux runs run 59 results final and GDS, right? So once you go here, you can use something called klayout, which is part of the Docker image, and run the GDS file. So running this will show you this, right? Okay, I don't need this. Yeah, so this is the layout that's been generated. So using this as a reference, you can scale up with your own design, and you can mess around with the config, and you should end up somewhere here with this, right? So yes, there's also one other thing, which is the OpenLane. So one interactive mode. Okay, there is okay, let's take a look at that. So there's a way to run individual things, like individual steps within. So as you can see here, yeah, so run interactive mode. So you can only run certain steps within OpenLane as well, like step by step. Let's say you want to like step it like a debugger, like you want to go through each stage individually and check. You can definitely do that. So that's also a provision. I'm checking if I can show it to you. Oh yes, so here's how you run it. So yeah, you can, from here on you can give it, and like let's say you want to synthesize, you synthesize one by one, step by step, you can do it. So that's also a provision. I guess I have covered most of it. So yes, that's it for the video.
Okay, that wraps up the session. I hope this session was pretty helpful for you all, and you all will use Vitis and OpenLane to develop something cool. And yeah, I'd suggest you all take a look at the documentation for both. There are a lot of cool things that you can do with them for the hack as well, especially if you've chosen the framework pack. And yeah, if you do have any queries as such, you can reach out to either of us on Twitter. Um, these are our handles. If you want to, contribute to our open source repos, you can reach out to us on GitHub, uh, which is tagged here on the screen. And yeah, thank you guys. I hope this was informative and you all have a great day.